What about performance testing? And we brought that up for the second time. The point is to show you the performance test of the SDR. There is intermediate frequency RF part. The middle is connected by numerical IQ. For traditional radio frequency sending and receiving information, the test is relatively simple. What you need to pay attention to is the performance of the input and output of the RF version. But for SDR, one of its biggest features is the digitization of many intermediate frequencies. A lot of intermediate frequency processing is in our digital baseband section. At this time, if you only pay attention to the performance of the radio frequency board or the intermediate frequency board, it is not enough. In other words, some parameters cannot be directly characterized. So let's first look at what instruments we will use that may be involved in the testing process. For example, for launch tests, we can use a spectrum analyzer for reception demodulation. You can use the real net for calibration between channels, or testing of phase correlation parameters. For example, the characterization of some various parameters of the device. For the receiving end, you can also send the radio frequency signal in and use the spectrometer to test at the intermediate frequency. That includes some digital buses that might use an oscilloscope. Up there, there's a thing called digital IQ interface. This is actually a digital IQ interface, but the control of this IQ interface is not limited to our SBRP, which will be used during testing. Many times between sending and receiving messages, if it is an IQ signal in the middle. That also converts the radio frequency signal into an IQ signal format that the instrument can recognize. So how does this format work? Let me show you. Suppose this DUT is a SBRP, or a digital transceiver. So if you want to measure the IQ signal quality itself, good or bad, imagine that the daughter board of the RF in the picture just now has actually been digitized and given to the motherboard. The motherboard used an IQ signal before, so this IQ signal, traditionally our approach is definitely not to test it. Or when testing, just use the receiver for testing. And that brings up a problem. Is your signal quality good or bad? You can correct it with digital compensation. Is there a third-party observation method to see whether the digital intermediate frequency signal is good or bad? Either IQ signal is good or bad. You can use the interface board we just mentioned. This interface board is just a tool for protocol conversion. Can convert the RF IQ format into a format that the meter can recognize. Of course, this grid is recognized in both directions. Supports a variety of interface formats. Common digital IQ formats include CMOS, LOVTL, and LOVTS. And on the right there's a settings interface. You can set the clock rate, level form, and logic format. In this way, the digital intermediate frequency signal can be converted. So this is also a more important conversion work we need to do before testing. Okay, let's go back here and take a look at the transmitter test. What are the usual test scenarios for the transmitter test of SBRP? In the middle one, I took a radio station as a replacement for SBRP. This is actually a software radio station. So what does that look like for a whole machine test? I can send the audio source or data source to SBRP through this audio interface or data interface. Then SBRP modulates the baseband signal and it will emit. What is the quality of the transmitter? Through a spectrum or signal analyzer, it will have this IQ demodulation function. You can see the overall performance of the transmitter. This is a common, typical scenario. What's the second scenario? The need we talked about earlier involves transformation. If only the daughter board is measured. At this time, there is no baseband inside that can be used. Then who will give this base belt? You can use, say, you make an FPGA, or you can use standard sources. The standard signal source itself can generate a digital IQ interface similar to this. The digital IQ signal can be converted into a form that can be recognized by the radio frequency daughter board through this conversion box. In this case, all test instruments, emission instruments, including digital intermediate frequencies, use standard instruments. So at this point, I just need to evaluate the function of the intermediate frequency board of the intermediate frequency signal. So what if it is for this transmitter or radio frequency daughter board? It is nothing more than these two basic configurations. What are the common launch test projects? I won't expand on this. Conventional such as signal-to-noise power, that's for specific signals such as the Wi-Fi, 5 grams, 4 grams signals just mentioned. At this time, I may pay attention to some specific channels, including pilot channel, reference channel, broadcast channel, synchronization channel, etc. It's also detectable by this way of stripping the signal. What about the spectrum? The most important thing is the ACLR of all digital transmitters. And of course, launch templates, bandwidth usage, spurs, etc. The most crucial thing is the modulation quality of. The modulation quality is mainly concerned with the characteristics of FMEM, including IQ. In fact, this is also a core indicator that determines the quality of the signal sent by the transmitter, or the degree of deviation from the ideal symbolic sample. And then of course there's another class of systems, like TDD systems. For example, we in Luoguang have many such application cases of radar. A very common test signal in that application case is a pulse modulation signal, or a chirp signal, or a pulse compression signal, etc. This type of signal is usually paired with a pulse. We need to pay attention to, for example, what is the switching ratio? What is the power spectrum during switching? These are some of the projects we need to focus on. ACLR, you can take a look. Here's an example of a test result. Then what we are sending now is a 100 meters 5 grams NR signal. So what did ACLR mainly evaluate? You can take a look. When a useful channel is transmitted, the spectrum of adjacent or separated channels leaks. In fact, it also measures a nonlinear index of our whole machine. You can see it here, and you can read this result directly. What about the stray, if I need to see the stray performance of the transmitter? Under normal circumstances, it may be necessary to make SPRP work at full power or full gain. And what about at this point in time? If the transmission power is too large, it will cause the spectrum analyzer to be compressed after entering the spectrum analyzer. This is also a feature that all receivers have. Then you can use this trap to first limit the useful signal to a situation where it is not overloaded. At this time, the spurious signal can be better characterized by measuring it. Of course, as mentioned just now, there are analog and digital in the test waveform. So for analog, we focus more on things like FM, M, phase modulation, or SBS modulation, and things like that. That modulation quality test. If it is an analog modulation quality test, for a spectrum analyzer, it has the function of analog demodulation. The FM signal or the M signal can be separated from the modulated carrier. After stripping it out, you can see the modulation frequency, frequency modulation offset, including power and time domain waveforms. Now, it's very easy to look at signals, kind of like radio. And the quality of the digital bars we're talking about. The quality of that number bar, here is a screenshot of the test result. The top left is our constellation. And on the right, you see some basic information that we have about modulation. I also noticed that Luoguang also has options for our vector analysis. In fact, people are still more concerned about this key indicator, especially for this kind of FMEM, or the IQ offset below, etc. Including the lower right corner, we can also demodulate our symbol. You can see what its symbol looks like in the modulated signal. Okay, there is also a general-purpose OFDM modulation. Didn't Mr. Liu introduce it just now? They did OFDM modulation with SPRP. So why bring this up specifically? In fact, you will find that, whether it is Wi-Fi, 4 grams, 5 grams, including a lot of these satellite communications, this modulation of low-orbit satellites that we see now, eventually it all comes down to OFDM. Why is that? There are many reasons why I won't go into detail today. So if you need to pay attention, for example, how is the signal quality of USBRP transmitted under OFDM modulation? You can also see the modulation through demodulation options like this. And finally, there's the pulse signal and the throttle signal. What about the pulse signal? What I'm showing you here is a schematic of the time domain of the pulse signal. Actually, it's closed for a while and open for a while. So we usually have to look at what the pulse width is, what the period is during the modulation. Sometimes it goes up faster, or it goes down faster, if necessary. At this time parameters still need to be tested, such as rise and fall time, switching time, pulse delay. In addition to the time domain, power or frequency domain, you may also pay attention to some of his peak power or some overshoot, etc. And that includes radar. Might also pay attention to what the initial phase is like within each pulse. Or is there a phase shift between pulses? So although pulse modulation seems simple, just take a switch and turn it RF power on or off, but in fact most of the users we meet, the attention to the quality of the pulse signal is still relatively high. What about this kind of test? You can also take a look. What about specialized analyzer options like this? It can measure the pulse width, duty cycle, rise time, fall time, including pulse top drop of each pulse by itself. And the upside is that if I send multiple pulses, I can test a function called trend. Let's say you have 100 pulses. I can see how much the pulse width has changed with these 100 pulses. What is this initial phase of the pulse? So this is quite helpful for our radar test. And then finally, there's the knockdown signal. What about the so-called frequency conversion signal? It can be mainly summarized into two types. One is what we call frequency hopping signals, and the other one is what we call a chirp signal. What about these two? In our actual military communication or encrypted communication, it is used a lot. The traditional test method is generally to use a modulation rate analyzer to measure, demodulate it to see its frequency change or to see its time information. But the traditional modulation rate analyzer, usually its bandwidth is not too wide. However, with the development of radar or the improvement of resolution requirements, in fact, the demand for analytical bandwidth has also increased a lot. So the paradigm here is to use big bandwidth analytics to capture the signal across the bandwidth. So capture it and then post-process it to get a frequency hopping graph like this one. In fact, the most striking thing in this picture is this frequency hopping map. Waterfall charts have bounces back and forth between different frequencies. Of course, the current analytical instrument can also analyze the switching time in the jump, the residence time of each frequency point, and some of its modulation states. So this function is more helpful for this verification if you want to perform frequency hopping or linear frequency modulation. Okay, that was the launch test. What about the acceptance test? It's just that you can find out. I also broke it down into two test scenarios. One is the whole machine test. The test of the whole machine is to use the signal source to send and the software radio equipment to receive. After receiving it, it may be audio, it may be data, and it may be other signals. We need to do a statistical analysis of this signal. The same goes for the TRX daughter board, but you can take a look. Compared to the transmission, I just changed the position of the signal source and the spectrum meter in a different order. The signal source acts as a transmitting device and enters the reception of the daughter board. What about the IQ data sampled by the daughter board after receiving it, and then analyze it to the spectrum meter through IQ conversion? In that case, in fact, it is a reverse process with launch. What are the common test items for the receiver? The first is sensitivity, which is the most important. That includes adjacent channel selectivity, co-channel suppression, intermodulation suppression, blocking. Now, all of these tests are based on a metric, and that's how small the signal is. You can demodulate the signal or demodulate it correctly. That's actually what the receiver cares about the most. Of course, it also has some test parameters to see how the receiver works in the case of some interference. Let's take a look first. How is the received signal quality usually evaluated? Or how is the sensitivity evaluated? So before we talk about this evaluation of this sensitivity, maybe give you a few concepts. The first is BER, which you may often see, bit error rate. And what about some data? It's not just a bit. It functions as a resource block. And at this point, we call it the error rate. Then there's the frame deletion rate. Frame deletion rate is when errors are found and some frames need to be retransmitted. Of course, there are also per error rate and throughput rate. What is the core strategic idea? It uses a standard source device to transmit to a software radio for reception. Of course, the source of this transmitted data is usually a pseudo-random sequence. Why use tail random sequences? It is because the SDR receiver usually demodulates the transmitted RF signal into the original code stream, which is then returned to the transmitting device. It matches the transmitted pseudo-random sequence with the received pseudo-random sequence. That way, I know which bits are wrong. Error rates tell you how low a signal is and what errors happen. Therefore, all receiver tests are inseparable from the function of error statistics. For adjacent channel selection, it is actually a step closer on the previous basis. We know that after we get the sensitivity of the receiver, we usually get a jamming signal. Then this jamming signal is usually added after. We'll check again to see if the bit rate of the receiver has occurred, or how much the bit rate got worse, or when the jamming signal is added to a large size, the receiver will have an error. So this is equivalent to a higher requirement for the receiver. So why does this happen? Because for the receiver, the intermediate frequency filter designed by itself is usually ideal. That is, the interference signal of the adjacent channel signal usually does not enter the channel of the useful signal. But unfortunately, there is no such standard intermediate frequency filter. It must have some kind of spectrum broadening. Then this broadening of the spectrum will cause some neighboring interference to enter the useful signal. That useful signal is equivalent to adding some noise. The throughput or sensitivity will definitely decrease. And the same thing with blocking. Blocking is the exertion of a larger interfering signal next to the useful signal. But this jamming signal is usually a tone signal. Okay, that was a receiver test. That's in addition to receiver testing for a SDR B product or software radio product. There is a large number of clock or local oscillator signals inside. How is the quality of the local oscillator signal usually evaluated? The current mainstream or more authoritative testing methods are usually called cross-correlation methods. What is the cross-correlation method? A traditional spectrum analyzer or oscilloscope can also be used for this clock jitter test. But it had one big problem. That is, if there is mixing between the tested part and the measuring equipment. Then when measuring phase noise or jitter, you can imagine a scenario. The test equipment itself will also have a noise called noise ref 1. And actually, what is the result of the measured phase noise? It is the phase noise or jitter of the instrument itself superimposed on the phase noise and jitter of the DUT. There is no way to remove the reference noise of the instrument itself. So they came up with a new idea. After the phase noise of the key under test is input to the instrument, it is divided into two channels. After dividing into two channels, mix or phase check with two reference sources respectively. This PD is actually 90-degree phase detection. What about the phase detection? The result is the phase noise or jitter voltage. If you use it as an FFT, it is actually the phase noise curve. And what good is that? You know, for a DUT, the signal itself is known and determined. But for noise, the two noise sources must be unrelated and random. So I'm doing multiple averages or smooths when I'm doing correlation. The noise of this reference receiver itself is equivalent to being smoothed out. All that remains is noise. That is, only the phase noise of the dot itself. So the higher the average number of hits, you'll notice that the final test results will stabilize. This phase jitter of itself between the two channels will be removed. So this is also a common method of clock testing. It is also the most authoritative method. Here is a result curve of the phase noise test. So what you see here on the left is the phase noise. There is both phase noise and amplitude noise. What about the right? Of course, in many scenarios, we also need to simulate the local oscillator. When there is a problem with this receiving circuit, I'm not sure if the transmit-receive link is caused by a local oscillator clock signal, then I'll replace the local oscillator. Replace with what? Replace it with a signal noise source with good phase noise. In this case, it can also replace some local oscillator functions for verification. That was the local oscillator signal, and of course, amplifier testing. Then let me briefly tell you about it. Now, normally with an amplifier, we measure some gain or nonlinearity. It can also be measured with a real network or a spectrometer, such as M or M distortion, M or PM distortion. What about reception? You know the key component is low noise amplifier. The core metric of low noise amplifier is the noise figure. Datasheet should also display this indicator. How is the noise figure usually measured? Is to apply a noise voltage to the DUT with a noise head. And look at the cold and hot states. The so-called cold state is the output noise of the DUT when it is applied and not applied. The noise figure can be converted by calculation. Then of course there are other components as well. Is there a filter in the circuit? But this must be networked. Well, in some cases. I'm also picking up some of our mixers. Now, what about mixers? They'll be vector, they'll be scalar. I just need to measure the power between the radio frequency and the intermediate frequency. And some days, for example, for our MIMO system. For example, the 3980 we released today is known to be 8-channel. If there is a mixer inside, after the baseband adjusts it, if the phase between each mixer is inconsistent, you can imagine, could it also cause this shift in phase? So in many scenarios, like this TR component, multi-channel antenna, we'll pay attention to the phase consistency after frequency conversion between each channel. Of course, it is also possible to verify the phase difference between each channel or observe its long-term stability through the real network. And then finally, the ADA test. What about the DAC test? I can use the digital baseband to turn the DAC into an analog signal. What about this time? Through this signal analyzer, there are baseband analyzers and radio frequency analyzers. Observe its spurious and spurious dynamic range, etc. Of course, the signal source can also provide it as a clock signal. What about the ADC? We can also use our signal source, both for his sampling clock and as an RF signal, then input it into our ADC. Eventually, we will count some indicators like the spurious free endpoint range and significant digits just mentioned. What about the end and digital baseband testing? Then this one is more versatile, and that's what you can do with an oscilloscope. Software-defined radios have many of these protocol control signals inside them. That by analyzing his timing and this joint debugging between multiple channels. But there's a little bit more to it. Because our test often measures time domain, modulation domain, and even digital IQ. So it is more convenient to use the oscilloscope. Can be debugged in multiple domains. And then finally, that numeric IQ analysis and generation and analysis. Then this is it. I won't dwell on it anymore, because it is actually the same as the concept of digital baseband structure board we introduced at the beginning. Okay, thank you.